So yeah, this is a great session to have after lunch because I talk about math and measurements. So this is me. I am Adam Mufich. I'm with National Comfort Institute. We train a lot on airflow diagnosing airflow issues, solving comfort problems, refrigerant side performance, all kinds of stuff like that. I owned a contracting company. I said this a little bit in my last presentation, for 12 years out of the Chicagoland area. Actually, where's Gio? I saw him in here. He bought my company. That's the guy who bought the company. Cool that he's here, right? And then prior to that, I worked for my dad for quite a long time. I started off when I was like 10 years old, handing him screwdrivers, right? So I've been doing this for quite a long time. I think I've been doing it correctly for maybe 5 years. And if you guys have seen me I post a lot on social media. I go by the tagline, A-Team Adam. That was the company name, A-Team, Heating and Air. So yeah, I wanted to dive in a little bit start off very low level, total external static pressure. Do you guys all measure that on a normal basis? Yeah, all the time? Okay, cool. So you guys probably all have an understanding of what happens when you have high total external static pressure, right? You have high blower watt draw, nuisance limit trips. That's one of the biggest things. You see a lot of people that have, you have heat exchangers that go bad. I see it on Facebook all the time. People are like, oh, this furnace is a piece of junk, you know, this brand X, right? So I'm gonna install brand Y, the same size equipment. What do you think is gonna happen to the new system with low fan airflow? Same thing's gonna happen, right? So dive in a little bit. I'm gonna give a shout out to my two friends at ACA here, Ed and Wes. I learned a ton from Ed. You know, I consider Ed a mentor. I went to one of his trainings in DC, and he really helped me kind of move things to the next level. Sizing is huge. If you want to solve airflow issues, start with sizing the equipment correctly, right? That's number one. Blower motor failures, that's another huge thing. I know with ECM and that, when you have high static pressure, they don't work as well, they don't last as long with high static pressure as they did in the past. Frozen evaporator coils, noisy, you know, how many, I had this actually in my first house where when the furnace or AC would kick on, you would have to turn up the volume on the TV when you're sitting there watching TV at night. So if you wanted to get through a movie, you had to turn off the heater air, right? Or low equipment capacity. If you're measuring capacity, you know, you're using measure quick, you're, you know, checking actual temperatures, latent and sensible, you have low equipment capacity. And like I said, heat exchanger failures, compressor failures. I think that covers most of it, right? That's low airflow, high TESP. Do these sound familiar? Do you guys run into this on a normal basis? This is something that's pretty common, right? Yep. So what is CFM? What's CFM? 1 cubic foot of air, right? It's a box of air. It's just a box. You guys know Ty Branneman, right? He did an awesome video where he's like stacking boxes up. This is a cubic foot of air. You start thinking about how much air a blower motor has to move, it starts blowing your mind when you think about the weight of air, right? So a CFM is, you know, how many boxes you move in 1 minute. What is static pressure? What's static pressure? Yeah, it's the outward force. We're not talking about airflow movement, right? It's like if you blow up a balloon, you could measure the static pressure of the balloon, right? So it's how much pressure is in a duct. It's the outward force. And how do we measure static pressure? You guys say you all measure static pressure. We use a manometer, right? What is the unit that we measure static pressure in? Inches of water column. How does inches of water column, what does that measurement actually mean? Do you guys know? Exactly. So I'm going to tell you a very humbling story from when I first started. When I had no business working on furnaces or any kind of HVAC whatsoever. I was running a maintenance call for my dad, and I was working at an older gentleman's house. And basically I was doing a maintenance, dusting off the furnace, making it look pretty and that. And he's like, are you going to check the gas pressure? And I'm like, check the gas pressure? You know, I never heard of that. This was probably in the year 1999 or something like that. I didn't know what a manometer was at the time. He's like, let me show you something. He actually went over and he grabbed a piece of vinyl hose. He hooked it up to the gas valve for me, filled it with water, and we took and measured it with a ruler. And I was like, holy crap. I can't believe this guy just showed me this. But like I said, I had no business working on equipment at the time. It was a very humbling moment. And this is kind of like what that would look like, you know? They make older, this is what a manometer would look like years ago, a YouTube manometer. So when you're measuring static pressure, you have the outward force. We're trying not to measure velocity pressure, right? So if you look at a static pressure tip, it's actually closed off on the end. So we're measuring the outward force. And we're forcing down pressure on one side of the manometer. And then when you measure the return side, the exact opposite happens. It's a vacuum. We're sucking it up. So that was just a very quick, like, hey, let's get down and dirty. What is static pressure? This topic right here, I would have to say that this changed my career and made me a better technician than anything else. And Steve Rogers taught me this. Do you remember our video call? And it was funny because after you taught me that, I was like speechless and I was like, holy crap. Like, I can't believe I didn't know this before, right? So we're going to be talking about affinity laws, kind of like Buzz Lightyear, but not infinity, affinity. Affinity laws, we look at pump laws and also fan laws. So there's formulas that you could figure out different things depending on which affinity law that we're talking about, right? This kind of all started, which Steve, correct me if I'm wrong, this was my research on the topic. The whole start of this came about with the Buckingham pi theorem by Edgar Buckingham, which is impressive. I don't know, how old he was when this came about, but that kid, he looks younger than my son, right? I don't know. But yeah, it was first ever proven in 1878 by Joseph Bertrand, which he's got a face only a mother can love. So this is the math. This is what's going to put you guys to sleep. This is where the rubber meets the road, right? Fan law 1, 2, and 3, and pump law 1, 2, and 3. You could figure different things out by whichever fan law you're trying to work with, but we're going to focus on fan law 2 today. That's mostly for residential. Fan law 1 and 3 you would use for commercial, right? So I wanted to explain to you what this formula, the first time I saw it, I'm like, man, it's intimidating.
Is that salt and pepper?
I failed algebra in high school, and I'm looking at this formula. There's too many letters in there. So let's break this down a little bit. So we have our SP2. That's what static pressure we're trying to solve for. So the whole purpose of this formula is to figure out if I know my static pressure and I know what my airflow is, I could figure out what my new static pressure is going to be at a different airflow, right? So SP2 is what my predicted static pressure or pressure drop is going to be. SP1 is our measured duct pressure, TESP, or pressure drop. So we could use fan law 2 if we're looking at pressure drops across evaporator coils. We could use it for pressure drops across filters, although it's a little bit of a different nuance if we want to get it very exacting. And CFM2 is our desired airflow. So the way I always think about it, we have CFM2 on the top of our fraction. CFM1 is our measured or plotted. So we have our CFM1, that's what we're starting off with, and we know what our SP or our static pressure one is too. And then we want to figure out what is our new static pressure going to be. So when would you use this? Well, let's say you have a system that has low system airflow, right? And you're measuring your static pressures, and they're not terrible. Have you guys ever replaced a system? Let's say you have a 3-ton system with a PSC blower motor, and you install a new new furnace with variable speed motor on it, and then you start commissioning it, and the thing sounds like it's like a rocket ship gonna take off, right? And your static pressure is through the roof. That's what we're going to try to figure out here. Like, how can we prevent that from happening? Because I'll tell you, like, that would ruin my day. I never understood why, but once you figure out that static pressure and airflow, they move together, but they don't move together. Like, if you increase airflow, you increase static pressure more. If you decrease airflow, you decrease static pressure more. So if you start thinking about it that way, and we pay attention to what we're selecting when we're replacing equipment, we could plan for that. So that's these are the different pieces of the puzzle, right? And then this is my version of if you want it to look really simple. This is for all the people that failed algebra, right? If you want to break it down. This is what do I want divided by what do I have squared times our measured duct pressure. So that's the easiest way I can think about it, is you're trying to figure out, just to break it down, so you don't have all those extra numbers in there, right? What do I have? And then, so this is the different ways to use fan law 2. All right, so if you have a furnace or air handler that has a filter, right, and you're measuring the pressure drop across a filter, well, if you want to figure out if we have an 800 CFM unit, you're moving 800 CFM, and then you're going to increase it to 1200 CFM. What is that static pressure going to be? What is my pressure drop? It will increase quite a bit. But the opposite happens when you decrease the airflow, which is pretty cool. And that's when you're sizing equipment correctly, you could take advantage of downsizing, less required airflow, right? So here's this is just our filter pressure drop. We're taking the higher pressure minus the lower pressure. So our higher pressure is always near the fan, and our lowest pressure is on the opposite side of the filter. So in this, just to give you an idea, this is an example of how we would figure out what our pressure drop would be across a filter. We'd start off with, what is our current airflow? Now you could either measure the airflow or you could plot the airflow. I would say that if you're plotting fan airflow, you need to be very careful if you have a dirty system, because it's not going to be accurate, right? So our after filter pressure is negative 0.762, okay? Our before filter pressure is negative 0.183. We deduct the two. So one thing when you're figuring out pressure drop, TESP, it's absolute values. So you always want to get rid of the minus or plus sign, right? So our pressure drop on the filter is 0.579. That's a high pressure drop. Most systems are rated at a 1/2 inch, but that's not that uncommon. I see that's very, very frequent when you see a system, you know, I've seen 16 by 20 by 1 inch filters on a 5-ton system. So if we start trying to figure this out here, we look at fan law 2, and we look at our measured airflow, which is 1151, right? And our measured pressure drop across the filter is 0.579. Okay, so we have our two numbers that we're starting off with. This is the existing equipment, right? The existing airflow, the existing pressure drop. And then we're going to figure out, hey, we just properly sized the system, and we have a 2-ton that we installed here. So instead of having a 1151 CFM running through that filter, we reduced it to 800 CFM. Okay? So do the math, do the division, 0.695. You square that number. What do you get? 0.483. So we're going through this at a step-by-step process, and when you get to the end of the formula, you can see that static pressure drop across that filter. See how far it swung in the opposite direction. We reduced that static pressure drop, which that filter doesn't, it's still not great, but it doesn't nearly look as bad as it did when we had that 1151 CFM moving through the filter, right? So that's our new filter pressure drop. So our evaporator coil pressure drop. This is another fun one. Do you guys all look at rated pressure drop for evaporator coils? Do you look at the numbers? I always thought it was like a knee pad that came with the in the box, you know? You try to keep something clean. You put your sandwich on it at lunchtime. But there's actually like numbers in there that you could use, which is pretty cool. So your evaporator coil pressure drop, you take it, you're looking at before pressure, before evaporator, and after evaporator coil. This is in a gas furnace situation. Air handlers are completely different, right? We're not really paying attention as much to pressure drop across an evaporator coil, but let's say in this circumstance we're replacing a gas furnace, but we're keeping the AC. A homeowner didn't want to change the whole system, and they just want to do the furnace, right? So we want to figure out what is our static pressure, what's our pressure drop going to be on the new coil? So our current airflow, same as before, 1151. We look at our before coil pressure. It's positive because we're on the outlet side, the discharge side of the fan, right? So 0.292. And then we look at our after coil. Same thing. We're just figuring out our pressure drop. Get rid of the signs, it's absolute values. And our pressure drop is 0.245, right? Same thing. Let's go through real quick. I want to plug this in. I want to figure out same CFM. I want 800 CFM. I want 800 CFM. We're downsizing it to a 2-ton, right? Our furnace has less required airflow. Or let's say the system that was installed there, it was an actual 2-ton air conditioning system, right? The condenser was 2-ton, it had too much airflow to start off with. So we're gonna figure out what is our new pressure drop. Same thing, plug in the numbers. What do we have? 1151, that's what we start off with. That's our measure or plotted airflow of our existing system. And then we look at our pressure drop. And then what do we want? 800. And we just solve for it. The biggest mistake I see people doing when they start playing with fan law 2 is when they go to square the number, they multiply it times 2 instead of actually squaring it. You'd be surprised how many people do that, right? But you multiply the answer by itself. And then your new coil pressure drop is 0.118. And actually these numbers are numbers that I had in my phone that I took from a customer's house with a TrueFlow Grid. So these are all real number situations that I played with here. So TESP, okay, same type of deal. We have the incorrect airflow for the furnace. We're using all the same equipment, and we want to figure out what our new TESP would be with our existing filter and our existing coil. We're going through the exact same situation. After we get to this point, I'm going to show you guys how to retrofit a job. That was game-changing for me, but I just want to show you a step-by-step process for each one of the different situations that you could use it for. So still, once again, we have our 1151 CFM. That's our measure or plotted fan airflow, and our after filter is minus 0.762. Our before coil is plus 292. Get rid of our signs and add them together, and that's our total external static pressure. Is that a very common static pressure that you guys see? Yeah. What do you guys notice? Like, what's average for static pressure? 0.8? Yeah. I think with like ECM blower motors and variable speed, you're close to 1 inch almost all the time, especially if people aren't paying attention to this type of stuff, right? One of the things that I've noticed is when you are, what I fell victim to selling residential equipment was if you needed to replace equipment for somebody and you're like, I need a 3-ton coil. I need a 3-ton coil. I need a 60,000 or 80,000 BTU furnace. They would give you whatever coil they want, they had off the shelf. So I would always try to pay attention to what is the rated pressure drop of that coil? You look at the AHRI matchups, right? And you want to make sure that you could actually have a matched system, and you're also really paying attention to that pressure drop of the coil. So to get back into this example, we want 800 again. We're solving for TESP. This is a cool situation, guys. We have too much airflow, and this shows what happens to our TESP when we reduce our required airflow. Right? 1151 again. 1.054, that's our measured static pressure, our measured TESP. And then we're solving for 800 once again. We do the math, and boom. Now all of a sudden we have, look at how much more the pendulum swung in the opposite direction. We went from almost three tons of air. So how often do you find a variable speed furnace not set up and it's just maxed out on high speed airflow, right? So if you have a 3-ton drive installed in a system that is a 2-ton, your static pressure is off the rails. And then you dial it in, and then all of a sudden, it's not so bad anymore, right? Look at how far it swings in the opposite direction. So this next situation here, we're going to look at duct pressures. This really changed the way I looked at everything. And I would have to say that the situations where you would run into and you would start, replacing like-for-like equipment and you weren't planning for your pressure drops. I know there's a lot of times in NCI, we talk about duct system optimization. We teach you how to actually look at existing ductwork and make little alterations in that to reduce your static pressure and increase your delivered airflow. Well, if you really start paying attention to fan airflow, static pressures, and selecting your filters and your evaporator coil, you can start planning for some of this stuff, and at least you're going to deliver the correct amount of airflow through the equipment and have good static pressures. They're within the manufacturer's specs. So the easiest way, and my favorite way, and I don't get paid from the Energy Conservatory, although if you want to start sending me checks, I wouldn't I wouldn't turn them down, is the TrueFlow Grid. I went on it's funny, I went on the waiting list when it was first coming out. I was one of the first people on the first order to pick up a TrueFlow Grid. And I was bugging Steve, like, when is it going to come out? When is it going to come out? Finally, they sent it to me, and I looked at it, and I was like, this is kind of scary. Like, this is before any videos existed or anything else. I'm like, I don't know how to use this freaking thing. And it sat in the box for maybe a good month or two. And then Steve came on, we have a YouTube show we do. Steve came on the show, and I'm like, let's try it out right live on the internet, right? And I put it in, and Steve's like, you have the manometer backwards. Like, it's hooked up backwards. Okay. Thanks, Steve.
That was a good Steve impersonation.
Yeah. Well, no, he said, I'll tell you what he said. He said, that's interesting. All right, so have you guys all plotted fan airflow before? Yeah, you've looked at plotted fan airflow. This table, the first time you look at it, it's overwhelming. And I remember probably when I was, I don't know, early 20s, I first started looking at it, I'm like, how the heck does this work? Actually, one of the guys that I learned static pressure from, I met him for the first time. On YouTube, I learned it from. He's here today. Pretty cool. Ralph Wolf. But this is a fan table, right? Basically, you just take your total external static pressure, you line it up across the top, and you look at what the fan speed is. So we have an F05 fan speed, and then you could determine you have 860 CFM. So, using fan law 2 in this situation, here, this is our numbers, right? Our supply duct pressure, our return duct pressure. Magically, we have the same pressure on both sides, which that never happens, right? But we're going to figure out, we want to figure out, our step-by-step is we want to figure out what is our duct pressure. When we're replacing equipment, that's our starting point no matter what, because we don't really care about, if we were changing a full system, we don't care about what the pressure drops are on the evaporator coil. And if you guys are doing it right, you shouldn't be paying attention to what the pressures are in the filter because you're going to be looking at resizing that filter for something with a lower pressure drop, right? So our new system is 1,000 CFM, and our measured airflow is 860. So now we're going in the opposite direction. We're increasing the airflow. We're installing a 2.5 ton system. We have our new system. What do we want is on the top, 1,000 CFM. That's what we want. What do we have on the bottom? 860 CFM. And our measured duct pressure is 0.15. We go through the math on it. Don't forget the square, multiply it times itself. We multiply 0.15, our measured duct pressure, times 1.35, and we get 0.2. So our new duct pressure went up, right? It went up quite a bit. So our duct pressure at 1,000 CFM is 0.2. We started off with 0.15 in our duct pressure. That was our original airflow. Our new airflow is 1,000. You can see that our duct pressure, just to give you a visual, our duct pressure increased on both sides. All right, so what do you guys think is going to happen? What can we do with this? If we increased our supply duct pressure and our return duct pressure, is 0.2, would you guys say 0.2 is a good supply or return duct pressure? It's not bad. But what happens when you start throwing a new evaporator coil and the pressure drop of the evaporator coil or the filter on it? Depending on what the pressure drop is on those, your static pressure could start increasing exponentially, right? So here's a rating. I took one easy rating. I know the chart could be overwhelming, that knee pad, but here's just one snippet. This is an Amana Goodman coil. So we look at our pressure drop ratings on the coil. 2.5 ton unit, 1,000 CFM, right? We're looking at 0.2 pressure drop across that filter. So now we're selecting the evaporator based on the lowest pressure drop for whatever AHRI matchup that we could find. So we're looking at multiple different evaporator coils to do so. We try to find the lowest one rated at our design airflow. And it's 0.2. So we start off with our supply duct pressure, which is 0.2. That's what we figured out is going to be with our new airflow. Our supply duct pressure is 0.2. Our new coil pressure drop is also 0.2, right? So what's our before coil measurement? How do you figure out your before coil measure? If we know our supply duct pressure and we know our pressure drop across the coil, this is a way of backing in to our total external static. So we're going to figure out what the total external static pressure is without any equipment in place, just looking at the duct system based on the ducts, right? So we add our pressure drop across the coil, and we take that and add it to our supply duct pressure. So our new before coil pressure is 0.4. And now we look at our filter. So most filters, if you start looking at them, first off, 1-inch filters, what are you guys normally seeing? What kind of pressure drops are you seeing on a 1-inch filter? And I guess it depends on what size, right? But when you start looking at pleated filters in that, are they good? It's a good pressure drop? What is a good pressure drop, right? So yeah, the lowest amount you can get. I've talked to people in the past, I'm like, what type of media filters do you guys install? Well, we do April Air, we do some 16 by 20s, we do 16 by 25s, we do 20 by 25s. And I said, eliminate all that stock and go to the bigger filters. Try to find the least pressure drop you could possibly find, right? So if you look at this situation, this is an April Air filter. This is a big filter. But 1,000 CFM has a pressure drop, a rated pressure drop, which you could actually find these. You got to dig a little bit to get the data on the filter ratings. But 0.4 pressure drop at 1,000 CFM. That's pretty low. So how do you find the after filter number? Well, we know what our new duct pressure is going to be. We started off with 0.15 return duct pressure, and we solve for our new airflow. So our new duct pressure is 0.20, and then we add our filter pressure drop, add it together, and we get a 0.24 after filter pressure. So how do you solve for TESP now, right? Well, we already solved for our before coil pressure, and we already solved for our after filter pressure. So we get rid of our signs, it's absolute pressure, right? Add them together, and look what happens. We have 0.64. Is that a bad static pressure for a gas furnace with an evaporator coil? Would you guys say that's bad? We're delivering our correct airflow, and our static pressure is 0.64. I mean, usually our rated is maybe 0.5, but I'm not gonna complain about this. I'm not gonna say, hey, you're gonna have issues, 0.64. That's not bad whatsoever, right? So we solve for that. 860 CFM. This is what I was trying to show you guys. When you have static pressure and airflow, they move in the same direction, but one moves farther than the other. So our CFM what started off at 860, and we had a 0.15 duct pressure. We increased our airflow to 1,000 CFM, and then we were at 0.2, right? So increasing the airflow by 16%, increase the static pressure by 33%. This is why if you're changing airflows, if you're altering what equipment is installed, you need to pay attention to this. Because look at how much more, what happens to the static pressure when we increase our airflow. This is an example, I fell victim to this so many times in the past. This is what happens when you guess when you're selecting components. So you have we start off again with our 0.2 supply duct pressure, and we have 1,000 CFM, right? Look at this coil. This is a different coil now, a different Amana and Goodman coil. Look at the pressure drop on that coil, 0.379. This is a coil that you would call the supply house, and you say, hey, I need a, whatever this is, 2-ton coil, ton and a half coil. This is what they give you, something 0.379 pressure drop. Once again, you add those numbers together, our 0.2 duct pressure plus our before filter pressure, 0.38, and we get our before coil number, 0.58. So now, just by changing the coil and not selecting the proper coil, we're almost at the same static pressure that we were at selecting a good coil, a more effective coil, right? And we're not even halfway done. We have to look at the return side and the filter.
I'm an educator, work at Johnstone Supply. Most of the guys in this room, guys and girls, are here because they know it, they understand it, right? So most times guys are calling up and saying, I need a 2.5-ton system matched with the cheapest coil that you can get me 17.5 wide, okay? That same coil may be available in 3 different slab sizes.
Yep.
No one ever asked for the lowest pressure drop on a system.
That's it.
No one. I know it. So the idea is that, these guys would be able to look that up. I try to teach the same thing, that when you're trying to size equipment, talking to the salespeople, look at what you're purchasing, because even though it's an AHRI matchup, look at what your statics are on that system, because if your duct system's not going to be able to handle that, please go with the larger coil with that less or lower pressure drop.
Yeah, exactly. And I wasn't trying to say anything bad about Supply House. I'm just saying, like, the counter guys are not designers. And they don't know what your static pressure starting point is, so they don't know what you're looking for, right? But yeah, you need to start paying. And just because you have a 17.5-inch wide cabinet doesn't mean you need a 17.5-inch wide evaporator coil. You can go with a 21, right?
Oh, no, they don't want to.
Yeah, you need a little transition. I know they make pre-made transitions if you want, right? But getting back to this, we're looking at, this is a different filter now. This is just selecting an Aprilaire media. This is an off-the-shelf, something that we had in stock, at our company, all right? So this is, once again, 1,000 CFM. The pressure drop on this filter is 0.22. Our other filter that we hand-selected was a 0.04 pressure drop. So look at the difference in pressure drop, quite a significant difference. So we add those together. Once again, our return duct pressure is 0.2, and our filter pressure drop is 0.22. So solve for that, add them together, and we have a 0.42 pressure drop, or a return duct, or after filter pressure. Our after filter pressure is 0.42. So this situation is just guessing. What happens when we just arbitrarily select components? 0.42 after filter. And now we look at, what are we doing here? We're adding our before coil pressure and we're adding our after filter pressure. Same equipment, same design airflow, right? 1 inch of static. We have the same capacity system. There's no difference in what we're doing here. All we're doing is we're hand selecting our evaporator coil and we're hand selecting our filter. And by doing so, we could drastically reduce our static pressure of our system. And in some cases, you're gonna have fans that will not deliver the required fan airflow at higher static pressures, right? So by selecting things in a certain way, you're going to extend the life of that equipment. You're going to have a lot less issues. I think a lot of times we're not really analyzing the ductwork and the static pressures and that of what's happening in the real life situation of the house. And we're just replacing things, and that's the issue. Biggest thing though is dropping the required airflow. When we pay attention to sizing, and I know you guys, conduits here, quick models here, there's all these different companies that we could use to try to figure out what our load is. Paying attention to the load is going to increase comfort. You're going to reduce your duct pressure, you're going to reduce duct leakage, and you're going to swing that pendulum much farther in the correct direction by installing a smaller system. So our recap, issues caused by low airflow and high static. Static pressure, right? We talked about static pressure. What is static pressure? I talked about how the first time I ever measured any kind of pressure, inches of water column, a homeowner taught me how to do it, which was embarrassing. Airflow, right? CFM, what is airflow? Static pressure and airflow are not proportional. You're gonna have the static pressure move a lot farther in one direction than the other. So paying attention to design, it's a pretty big deal. This is, I know a lot of times we badmouth equipment, we badmouth manufacturers, it's a piece of junk, this carrier, this train, this Lennox, whatever it is. But if we're not paying attention to how the equipment is operating and under what conditions, we're gonna continue having the same thing and recurring problems over and over again. So yeah, we looked at fan filter pressure drop at different airflows, evaporator coil pressure drop, and all the different scenarios. Total external static pressure at different airflows, right? And then the biggest one, backing into a TSP with duct pressures. That's my favorite thing. I would spend the time to do that, and that really changed the outcome of my installs. I would say that I would have a hard time sleeping at night when I install the system and it sounded like a rocket ship. I just felt defeated, right? I always, my biggest thing was I took pride in the way things looked. The guy that taught me sheet metal, he's probably 89 years old now. He's amazing, he's a craftsman. So I was always taught to try to make things look right, do things right, use a Pittsburgh machine, you're using a brake, we had a sheet metal shop, right? Make all your pipes straight. But once you start measuring how equipment is operating and actually commissioning things properly, it's a whole nother ballgame because you get kind of your butt handed to you if you're not figuring out if your equipment's operating the way it should. So I know I'm finishing probably way early, but NCI, who is NCI? I work for National Comfort Institute. It's an amazing company. We try to elevate contractors. We teach a lot about airflow, how to diagnose airflow issues, how to go into a home and redesign a duct system, not from scratch, but making small changes to the existing ductwork and increasing the airflows to the areas we need. We teach air balancing, carbon monoxide, combustion, that's the biggest one. I don't know if you guys have ever been through Jim Davis's training. I was lucky enough to actually experience that. He's like the granddaddy of combustion. But the whole thing is, you guys, if you need anything, call me. I would love to walk you through this, and if you want a copy of the slides, I'd also give you that. I want you guys to start using this, and even if you don't start using it today or tomorrow, just that you know it exists, you can go up and re-look at it in the future. This will change the way you install residential equipment. Thank you.
Thanks for watching. If you're willing, give this video a thumbs up and drop us a comment. Don't forget to hit that bell icon to stay updated with all of our future videos. And as a quick reminder, HVAC School isn't just a YouTube channel. Dive deeper with us at our main website, hvacrschool.com. Curious for more knowledge on the go? We've got you covered. Tune into the HVAC School podcast, available on all your favorite podcast apps. And while you're at it, join our thriving Facebook group. Also, don't miss out on our free mobile applications available for both iPhone and Android. We're all about community. For techs, by techs.